Hello and welcome to today's video. So we are going to learn how errors propagate in powers. I'm sure many of us have been waiting to see solutions to problems of this sort. Well, you're at the right place today. Don't forget to share and subscribe and hit the notification bell. So we're going to learn how powers propagate, errors propagate in powers. These are one of the simplest and easiest when you get to know it. Now the findings from the first part of this problem, we are going to use it in evaluating the second part. We want to be able to calculate the relative error when we evaluate power approximations. So let's quickly dive in. From the first part, assuming x, a quantity x is represented by small letter x plus delta x, what is the error in the approximation of x to the power of n, where n is the power of x? So we are going to do it step by step. So we are giving x is x plus or minus delta x. So to find error in x to the power of n, so we are going to see that let z plus or minus delta z be x to the power of n. So whatever we get as x to the power of n, we are according it to z. In other words, z plus or minus delta z is equal to, so x itself is x plus or minus delta x to the power of n. Okay, so this is where your binomial theory comes in handy. Now the binomial theory that I'm going to use is this. Follow me. So I remember that a plus b raised to the power of n is given by a raised to the power of n, then plus n b, I have plus n, then I have a raised to the power of n minus 1 and b raised to the power of n, and plus n into n minus 1 over 2 factorial, then I have a to the n minus 2, b to the 2, so this is b raised to the power of 1, and plus n into n minus 1, then n minus 2 over 3 factorial, then I have a n minus 3b to the 3 plus dot dot dot. So this is the binomial theorem I'm going to use for this side. Please don't be overwhelmed. You don't need all of this, but you just need to wait till you see the results. It's really amazing. So z plus delta z in this case is going to be, so this is still the same thing as we having x plus, let me say, plus or minus delta x. Is that okay? So to the power of n. So this is what I am going to have eventually. So if I expand the brackets, taking x to be a and taking b to be plus or minus delta x, this is what we're going to have. We're going to have x raised to the power of n, then plus I have n, then a in this case is, remember, x, you have x to the n minus 1, then you have b is plus or minus delta x to the power of 1, and plus I have n minus 1 over 2 factorial, then I have x to the n minus 2, and b is plus or minus delta x to the 2 plus dot dot dot. So this is where I'm stopping. Now something amazing happens. We've already learned that delta x is very small. So all the terms in delta x raised to the power of n such that n is greater than 1, all of them will actually tend to 0. So all the likes of delta x squared, delta x cubed, delta x4 and so on, all of them, they are going to be very, very small. So we can neglect it. So I'm going to neglect starting from this term till the end of this series. I don't care where it ends, but I'm going to neglect it. So the reason I'm neglecting it is because when you open this place, you see that delta x will be squared. In the next term, delta x will be cubed. So the only term that survives is actually this one over here. Is that okay? So my z plus or minus delta z in this case is x to the power of n, then plus n x to the n minus 1, then I have plus minus delta x. Now if we rearrange this particular mathematics very well, we are going to get x to the power of n plus or minus n x to the n minus 1, then we now have delta x, because basically these terms are kind of like constants in a way. Okay, so they are constants, that's why we can do this easily. Now this is what we've gotten. Is that okay? We've gotten that for these two equations, when you compare the measured value parts and the absolute error parts, the measured value part is z corresponds to x to the power of n. That's this part, then this part, then this is your plus or minus, then this is the absolute value part. So the absolute error, absolute value, absolute error parts now correspond to this guy over here, x n minus 1 delta x, like this. Is that okay? So the absolute error part corresponds to this particular one. So if you want to find relative error, how do you find relative error? You find relative error by taking the ratio of what? Delta z to z. Is that okay? That's precision relative error, if you remember. So relative error is delta z over z, that's absolute value over measured value, which in our case we've already gotten as this. So we have nx to the n minus 1 and delta x divided by x to the power of n. So if we evaluate this, the law of indices is going to play here. When you have x to the n minus 1 divided by x to the n, x to the n cancels out x to the n and you're left with x to the minus 1. Is that okay? So that's x to the, let me just simplify it slowly, x to the n dot x to the minus 1 divided by x to the n, because according to law of indices, x to the n minus 1 is x to the n dot x minus 1. So when they cancel out, you'll be left with x to the minus 1. So I have n x to the minus 1 delta x, okay, and delta z over z is equal to the golden formula. N is a constant, so it can, well, let me just leave it there. It will be n, so delta x over x. According to the law of indices, x inverse x to the power of minus 1 is still the same thing as 1 over x. So this one can translate to the denominator and be in this form. So this is the formula that is associated with calculating relative errors for powers. Okay, this is how errors distribute in power. So for a given x, right, x plus or minus delta x, our x raised to the power of n have a relative error corresponding to delta z over z, and that's equal to modulus of n delta x over x. Okay, so this is how we calculate it. So we just need to substitute n, then our delta x is the absolute error, then x is the measured value, and this is how we can calculate the relative error in solving for x. So let's apply it to the examples that we're giving. So if 2.034 is an approximation to x, then find the relative value error in x to the 4 and cube root of x. So we have given that small letter x, okay, is 2.034. So anytime they say something is an approximation to a capital letter, I'll just label it as a small letter. So this is the small letter version. Is that okay? So they now want me to find the first part is x to the power of what? 4, and the b part is cube root of x. So of course in this particular problem we have to point out our variables. Relative error delta z over z is solved by n delta x over x. Is that okay? So we are looking for n, which is already in the first case. In the first case n is 4. So how about delta x? How do we find delta x? Well, remember what we said about our greatest possible error. Anytime we are not giving an absolute error, okay, anytime you're not giving absolute error, you can use your delta x to be the greatest positive error, which in this case is actually dependent on the current state of x. Now x has 3 decimal places, so it means that this function must have been rounded off to 3 decimal places. This particular expression, capital letter X, must have been rounded off to 3 decimal places of 4 significant figures. But I'll use 3 decimal places so that I'll have 0.5 times 10 to the power of minus 3 as my absolute value for x. So if I have it in this way, I now have everything I'm looking for. So my delta z over z is now going to be what? How do you calculate delta z over z? You have n, which in this case is 4, and modulus x is times 0.5 times 10 to the power of negative 3 all over x itself is actually what? 2.034, and this returns a 4 times 0.5 times 10 to the power of minus 3 all over 2.034. So we're going to toggle our on-screen calculator and see what this evaluates to. So we are actually evaluating a ratio 4 times 0.5 times 10 to the power of negative 3 divided by 2.034. So we have 0.000983 roughly. So this is the relative error. Is that okay? So if they want me to find the value itself, remember z can be gotten by saying x raised to the power of n. So there's a difference between the value and the relative error and the absolute error. So this over here is the relative error. Z to x raised to the power of n is the value, and in this case we have 2.034 to the power of 4. So what is this going to be? 2.034 to the power of 4. 17.1161 roughly. 17.116. Let me just write 05 9 7 6 8 3 4. So this is the value of z. Okay, so if you want to find absolute error, although they might not really ask us to find absolute error, but if you want to find it, absolute error is given to us as, of course, it's always going to be the magnitude of the product of z, which is x raised to the power of n, times the relative error that we just got in this place, right? ER. So we have the magnitude of 17.11605976834 times this value 0.000983. So let me just try to approximate it. So my absolute error is going to be, let me say 17.11. That's a 71. 17.11 6 0 6 multiplied by 0.009833, so 0.01683. So we can see that the measured value or the result z plus delta z, which is gotten when we raise x to the power of 4, corresponds to the value of z, which is 17.11606, and plus or minus the absolute error, which is 0.01683. Okay, so for the second one, let's solve it together. So for the b part, we want to solve the cube root of x. So of course you still remember what the cube root of x is according to law of indices. That's x to the power of 1 over 3. So in this case, our delta x still remains, since we have small letter x to be 2.034. I have 3 decimal places, so my delta x will be 0.5 times 10 to the power of minus 3. That's the greatest possible error, the greatest possible absolute error in delta x. So having gotten this value, so what remains is for me to now evaluate the relative error. That's delta z over z is equal to, according to the formula, n delta x over x, and this gives me n is 1 over 3 in this case, because n is equal to 1 over 3, it's the power of x, and times relative x is 0.5 times 10 to the power of minus 3 all over x itself is 2.034. So if we evaluate this, we're going to get sorry, I don't need the absolute value now. I have 1 times 0.5 times 10 to the power of minus 3 divided by 3 times 2.034. So let's evaluate this. So our relative error, delta z over z, is now going to be equal to, with calculator, I'll open a fraction. So 1 times 0.5 times 10 to the power of minus 3 divided by 3 times 2.034. So I have 8.194035 times 10 to the power of minus 5. So this is the relative error involved in this particular calculation. And if you want to find the absolute error and therefore the measured value, which is z plus or minus delta z, you can follow the steps I followed above so that you get your hands conversant with it. So that will be an assignment for you. I want you to determine the absolute error and give me the measured the approximated answer in terms of its measured value and its absolute error, and if possible go as far as determining tolerance interval. So this is it about propagation of errors and powers. I hope it was simple, and thank you for watching. See you next time.